Everybody, this is a late Christmas Eve recording of a lab report. I actually didn't intend to do this, but got caught up in working on some manual camera calibration techniques in Pix4D, and I wanted to get this out before I forget. So, before I do that, one fun little note. This is a neat little wind modeler I found that interacts with DEMs and is used to predict wildfire spread. It's a pretty neat idea, and yeah, I'd love to know more about it, but at least this is sort of a bookmark, and if people are into it, they can follow up on it. The two main things that I wanted to talk about today are this camera calibration issue, and then just a little bit that Gunjan and I worked on today. He'll probably report on that more fully later, but I had taken some notes in PowerPoint, so I just wanted to actually get these up there for his benefit, really. So before I begin, I'm going to talk a little bit about camera calibration. I just wanted to make a note here of some really great sensor sizes. This is a company that supplies targets to do camera calibrations. And probably it's for much more serious operations than ours, for-profit aircraft-based stuff, I imagine. But anyway, it's a super good detailed knowledge base, and so I'm making a note of it here. One of the things that I really liked about this is a description of different sensor sizes and their heights. This stuff can be super annoying to find, so this is just a nice little note. More information on that page. This is just a little snippet. Okay, so on to the main event, which is camera calibration. So we've talked about many times when we're doing structure from motion reconstructions, the camera model, the sort of physics-based description of the camera lens and the camera sensor is important. Without that, you can end up with images that just aren't right. They warp. They don't maybe come together well. All sorts of sort of little problems that happen as a result of poor camera models. Most of the time, you'll experience that as Pix4D didn't run. Your cameras didn't calibrate. And so what I'm going to talk about here is a manual method of doing that. Whenever you run Pix4D, it will actually try to calibrate your camera as it goes. Which is neat. It's sort of calibrating your camera and it's figuring out where your cameras are at the same time. But if you can come up with a correct model of your camera, then that's less work that Pix4D has to do. There's less uncertainty in the model, and hopefully that will translate to faster runs, more accurate runs, fewer problems, and so on. The camera database that exists in Pix4D is fairly error-prone. We've documented at least, I think, 5 different cameras that we use in the lab that have problems in the database. And probably they don't care too much because, again, you're supposed to be able to kind of calibrate these things while you fly. It's not supposed to take an extra step. Agisoft, Agisoft actually does this differently. So Agisoft Metashape is a competitor to Pix4D. And they do sort of feature a camera calibration tool, and they want you to do that separately. I think that's wise, so I think this is a good step. I actually tried to use Agisoft's to do this, although they do support a wide variety of cameras. They don't. I couldn't figure out how to get the fisheye camera calibration routine to go. I figured it out for sort of a normal camera, but I couldn't make it work for the fisheye stuff. So. Documentation seems a little bit poor for Agisoft. I'm not. That's not a definitive statement. I'm still a total newbie, but I did have a hard time figuring out what I was supposed to do. So there are a couple of options. Jack has mentioned many times that there's a MATLAB based camera calibration toolbox available. Caltech puts this out. At least I think this is the same one that Jack's talking about. And I put the link in here, and I've updated the wiki under Structure from Motion with all of this stuff. It seems like it's still there. I didn't try it. I don't have MATLAB on my computer. I'd have to remote in and lots of other stuff. It does say on this that it's been ported to OpenCV, which is great. So that would make life easier. And there's, I think that's something that we should pursue, because the method I'm going to describe here is going to use Pix40, which I think works, and it should. But it would be nice to sort of try some of these out. Along the way, I also discovered that MATLAB has its own neat, great toolbox. So I think they've basically taken that Caltech toolbox and scooped it and pulled it into MATLAB. I don't know if we have a license for this. I don't know either way. And again, I don't have MATLAB on my own machine at home, so we'd have to do this in the lab, which is fine. But I just sort of set this aside for now. I'm interested in following up on that at some point. Again, Agisoft has this, but I couldn't make that work. And then the general method that's being described here is usually this paper by Zhang in 2000 is kind of the gold standard for this work. There's a newer paper by Tan et al. From 2017 that describes a newer way of doing it with a computer screen. And from what I can tell, that actually works a little bit better. There's some neat advantages to that. One of which is that a screen is always flat. Well, a flat screen is always flat, and so that does constrain the error a little bit. So that's great. Again, all of this stuff is up on the Structure for Motion page, and we're going to be using a calibration target. Lots of different utilities will make these. This is just a checkerboard pattern. There's some other interesting, cool circle ones and some 3D ones. This might be fun to play with sometime. But anyway, this is the one right here. Caltech puts this out as a PDF. I rendered that using GIMP as a PNG, which I'll talk about here in a second, and that is posted to the wiki. Okay, so here's the way that this works. Basically, what you want to do is use this one of these test images, these checkerboards. The one that I have, again, I took the PDF from Caltech, and I used GIMP, and I rendered it out to 1920 by 1080. And what that gets us is a very fixed, known size. Now, probably, strictly speaking, that's not necessary. I don't think that it has to match your resolution of your monitor. But it might be a good idea. And actually, come to think of this, this is technically not a 1920 by 1080. It's 1080 pixels high, but it's not 1920 wide. So it's a bit of a misnomer. Anyway, then what you do is you look up the size of your the active display size of your monitor. So in my case, I've got a little screenshot of that from the documentation online. I've got a Samsung 27-inch monitor, and if you look this up, it says that the active display size, so this is in the lower left of that little paste, is 597.6 millimeters by 336.15 millimeters. So you can get this quite precisely. The image that that Caltech distributes has these 30 millimeter squares when you print it out correctly on an 8.5 by 11 piece of paper. So and it's got a little white border around it. And the squares themselves are supposed to be 30 millimeters. So if you divide that 8.5 inches, so that's the short side of the paper, and then divide the active height by that. So mine was 336.15. You'll get this ratio of how much bigger or smaller your screen is than that page. So mine is 1.55697 times bigger than the paper. I will mention here that I think it's probably the case that the bigger the screen you do it on this, the better this is going to work. Yeah, hopefully that's true. I guess we'll find out a little bit later on. So then what you do is you take that image and you open it in Windows, just using whatever, and I just use the default image browser. Make it full screen so that it's taking up the whole thing, and then just do a spot check to make sure that, sanity check to make sure that your calculations are correct. So you can see here what this looks like on my screen with the ruler. Remember that we're not sort of getting an overhead view, but that pretty much checks out. You can see from the picture that pretty much checks out as about 46 point something. It's a little bit over 46, I think you can see from the image. So the math says it should be 46.709, so that seems correct. Then what you do is you calculate where the corners would be. So this is a 7 by 9 squares. So then you just multiply that 46.709 times 7 or times 9 to get that. So my screen is 326.963. The difference between the corners of the squares, let me put it that way, is about that. And that should be then a little bit smaller than your active height, which also checks out. So that's about 1 centimeter less than the active height, which looks about right to me. And then the long edge would be 420.381. So this is what you're going to use later in Pix4D to mark ground control points effectively. You're going to use this checkerboard as ground control points. So then you take a bunch of images with your camera, and a bunch of images. I don't even know what the right number here is. I think this is 20-something images. And then you run Pix4D with it. And so I just set it to an arbitrary coordinate system. I used a camera model that was pretty close. You do want to make sure that your sensor size and your pixel size are correct. So sometimes with our stuff there's some uncertainty there, which is frustrating. The Mavic 2's image sensor is still a bit of a mystery in terms of what that is, but hopefully we'll figure that out sometime. But anyway, then we essentially run the model. It should calibrate. It's not a particularly hard problem, so you should be able to get a model out of that. And then what I did is just add manual tie points to the corners of the checkerboard, just each of the 4 corners of the 7 by 9. I marked all of the images, so you can see 27 images are marked in each of those 4 corners, and then I re-optimized. And then I went in and changed the MTPs to GCPs, and then set the coordinates according to those numbers that I found. You do want to make sure that you're setting your, remember that you're in meters here. So 0.42 is 42 centimeters. That's still within a millimeter. The right value was, I forget, 420 something, and I rounded down. Anyway, I put these in there. Also make sure that I'm setting these as X and Z coordinates. So the X coordinate is, the long edge, so that's the 420. And then the Z, because my monitor is kind of facing, is facing outward, it's going upward, so 327. So you just get those set the way they go, and then re-optimize those. I also needed to re-optimize because I forgot to set the global shutter to fast, which is appropriate if you are taking pictures from a more or less still vantage point, or at least not much change given your distance to target. Anyway, then you can load and save those into your camera database, and then you're done. So I've got a picture of what that looks like. So these are the old values at the left that I started with. Not bad starting values, but you can see that there is a reasonable departure for all of these values, and I think that that's going to make for a better model. Time will tell. So this is all stuff kind of done in the lab. We need to field test this and see if we actually get better models out of this. So the impetus for this is that Lynn Resler's models, when I ran those, are quite curved, and almost certainly that's because of a bad camera model. So I want to rerun those with a better camera model. So hopefully we can tune things up a little bit and make some big improvements there, and everything will be better. Okay, and then this is for Gunjan. Gunjan and I met today, our usual kind of one-on-one. So this is mostly for him. But one of the things that he's working on is trying to figure out how we're going to assess these these thermal maps. And one way that we think we can do it is by basically comparing these things to topographic maps. So a thermal map has a value that changes in space, just like sort of elevations do. You can imagine both as sort of 2.5D surfaces. And so maybe the idea is that sort of some of the tasks that are used to assess map knowledge for topography and terrain would translate. Now here they're working, this map assessment was created a few years ago to sort of test people's understandings of how well they read topo maps. So here we're talking about contour lines specifically, but I think that these probably extend into other kinds of systems as well. Anyway, so there's a bunch of ways to do this. The TPA is itself online. I have a copy of something that a modified version of this that Nicole Ledoux gave me that we can use if we decide to put that in there. But here we're just sort of looking at some tasks. So I'm just going to focus on the tasks that are going to look like they're going to work pretty well. The first is something like this. So it says, given you're at point A, what's the elevation at A, and the corresponding task would be, show them a thermal map and then mark a point and then say what's the temperature here. This one is drawing 4 points and then a line that connects them. And basically you're saying what's the steeper gradient. So I think that should probably work. That's a neat one. That sort of asks you to interpret the pattern along a part of a map. So I do like this one a fair bit. This one is a nice little pairwise comparison. So which elevation is higher, A or B? That's easy to do on a thermal map. Plunk down 2 points, which is hotter. And then this one is the profile estimation task, and I like this one a lot. I basically did something like this on a lot of the tests that I ran when I was testing the LiDAR visualizations that I came up with. So here, going from A to B, which of these profiles is correct? So you just have to match them up. Pretty easy. The big kind of mystery, though, is what we're going to do about 3D. This is just a little 3D reconstruction of part of Wallace Hall. So we're going to be, I do hope that we're going to have building facades and not just an orthophoto. That's part of the whole point. But I think we could probably do A/B comparisons, and I think we could do profiles. I'm not quite sure how to make that happen, but maybe poetry would be useful here. Maybe PsychoJS or something might be helpful here. I don't really know for sure. But anyway, that's it. I just wanted to get this recorded before I forget. That is now done. I hope you all have a nice break, and we'll see you soon. Bye.